Our second speaker is Uroš Kranjc. He is a research fellow at Institute of Philosophy, Scientific Research Center of the Slovenian Academy of Sciences and Arts. He is also a former Marie Sklodowska-Curie Actions Fellow at the University of York in the UK. His research interests are the critique of political economy, history and methodology of economic thought, and contemporary philosophy. His most recent work has been published in the journal Philosophical Economics, Critique, and Cosmos and History. Thank you.
Thank you. Yes, first of all, thank you for your invitation for, I guess, mine a little bit out of the box research topics that I have. So hopefully it'll come interesting to this audience as well. Yes, so the title that I proposed is Number and Function, or Numbers and Functions, Traversing the Economic or Economical, Mathematical and Philosophical Discourses. So, as you might have guessed from this title of the paper, my main topic of today's talk will be about mathematics, or more precisely about history of mathematics and philosophy of mathematics. I hope, however, that a certain trajectory will also be made visible, one that should connect on one side philosophy and on the other mathematics and economics, as the title suggests. So this talk will be roughly divided into three subparts. The first part, a very general and short introduction of some contemporary, let's say, French philosophers on which mathematics has made the most profound impact, and vice versa, those that can be most credited for the revival of mathematical discourse in philosophy, namely Alain Badiou, Cornelius Castoriadis, and Gilles Deleuze. For the second part of my talk, I will try to give a snapshot of the evolution of concepts, number and function, that range roughly from Plato and Aristotle to early modern period of Newton and Leibniz. This is when the mathematical function, as we know it today, was actually introduced. And in the third and concluding part, I aim to very superficially introduce the contemporary definitions of these discussed concepts of number and function, and show how can they be traced also in the discourse of economics, prior to, let's say, Adam Smith's foundational study of the wealth of nations. And after that, I hope we can all give some avenues on how to reflect further on these progressions done by contemporary mathematics. So first, to these contemporary philosophers, what actually binds all this edifice together? It is, of course, the notion of the multiplicity, the manifold, or the ensemble. The list of thinkers who are engaged in this debate is far too long, but for our trio here, let me just mention, at least on the mathematical side, of course, the name of Georg Cantor, and the names of Ernst Zermelo and Abraham Frankl. And on the philosophical side, of course, Edmund Husserl and Henri Bergson. So we are taught by these philosophers that what we have is an ontology of the multiple, as Badiou says, or that the philosophy is a theory of multiplicities, as Deleuze says, or that we have to think of being in general in its multiplicity, a thought by Castoriadis. So from here, the paths take their own courses, where with Badiou going for Zermelo-Frankl axiomatic set theory as the base model for his project of mathematics, his ontology. Deleuze investigates the crucial opposition in mathematics between the extensive multiples or sets and differential multiplicities. And while Castoriadis subsumes his inherited logic of today, and he uses the neologism of ensemblist, identitarian, or acidic logic, a logic that holds sway over our reality, and he does distinguish this from the magmatic character of indeterminate multiplicities that are reserved for the site of being. Now, what is at stake then? When Badiou says, and I quote, "Number is a form of multiple being with two components, or a pair, the ordinal as the material of the number, and a subset part of the ordinal as a form of the number." And he says, on some other occasion, an arrow as a function going from one object to another object. Or when Deleuze says, the concept of number is synthetic as it is originally intensive and vectorial, but also extensive and scalar, for it cancels this difference on another plane. And further, that the concept and function must intersect. And when Castoriadis maintains that neither the number nor space can be considered simply ensemblist identitarian, but intertwined in every effectively actual being and in being as such. And when he says that the units of the cardinal that are the moments of an ordinal coexist, meaning that they're mapped as an extension. So what can be made of all this? What questions were taken on to arrive at these propositions? What was the original object of inquiry? Now, it has been for some time now, and it still holds, that there can be absolutely no doubt about the universal reign of number today. Everything that counts and matters has to be counted, empirically or statistically, in order to exist, to be verified, or to have an impact in a state of affairs. In the final instance, to have a determinate value, to be determinable whether something is large or small, whether dense rather than scattered, meaning that it has to correspond to a given measure or ordering. Now, the counting and measuring of election votes, of exit polls, of referendum ballots are in principle no different than counting gross domestic product outputs, counting gold or cryptocurrency reserves, stock market prices or balances of payment, or further still, counting illegal immigrants, laborers without work permits, the shifts in distribution of cultural social identities, the casualties of wars, and so on. And may I remind you that just last week there was a document published by the European Union called the Draghi Report by Mario Draghi. And when you look at that document, you see there are practically more numbers than there are sentences describing how the future is going to be for the next 10 years in the European Union. So that is just another exposition of what the reign of number means. But they all are denumerable multiplicities, distributed according to a certain law or a function, from which we commonly derive, classify, or simply count for the needed majorities, for prevailing attitudes and opinions, or judgments of taste. Now, to sum up this particular trait of our current situation, and let us call it in the old terms, that of capitalist mode of production, or a newer Pont-Mentou word, the parliamentocracy, where we have all this counting performed according to a determinate universalization function. Now, what does this function actually do? To put it a little bit more mathematically, it maps according to some laws of determinate axiomatics or rules pertinent to presented objects from a domain, let's simply call it in curly brackets our common world, to a certain codomain, and let's call this in curly brackets our particular world in the middle of the third decade of the 21st century. And it does so in an endless repetitive representational recount of terms. Hence, it seems that we have always stumbled upon a consequent implication as to what the contemporary usage of number and numbers almost naturally relates to. That is the notion of a function. As with the ubiquity of the number, we can also easily infer the ubiquity of function. That is the courtesy of the invention of the propositional logic and of propositional functions, which are introduced by Bertrand Russell. And also, indeed, as in the case in the history of number valuation, so too, the notion of function has emerged in the contemporary general use as a propositional relation of objects in reference to a certain valuation of truths, of course. Now, consider its most commonly taught forms. We are taught in schools, for instance, the simple functional notation y equals some f from x, right? We all know that, or we know the other notation, the so-called arrow notation. You have an f and a semicolon x draws to a y with an arrow, right? You remember that as primary school. So what we have here given is a simple pair, and we have an independent and a dependent variable linked together with some correspondence relation. And this similar relation we can also encounter, for instance, in the axiom schema of separation in sets. Where we get out is the concept of extension in the predicate logic, a certain truth value function. Just to simplify, take a simple example as a preposition. For instance, Uroš is a human, and you have a simple function of the type P of X, x equals a, right? So is a human who the variable Uroš is a human, and we have a sort of predicate. So we can propose an unlimited number of such examples, to those more complicated with several independent or dependent variables. And of course, all these are the cases of propositional and predicate logic, of which the prime name, of course, as you all know, is Frege, where the codomain simply has the power of two objects, the true and the false, right? You all know that this is the verification function. But immediately, when we move from sentential logic to the first order logic and attain much more building blocks such as constants, variables, or predicates, we can also significantly expand our horizon of functions and operate with the functional, that is, of course, causal relationships we commonly learn in university courses, which is something general. For instance, when I was studying economics, you had a function of investments that is a function of the interest rate. Or when you go to sociology, you learn that ethnic segregation is a function of the relocation cascade. Or that in behavioral psychology, you have an environmental feedback function that is a two-sorted function of initial induction and covariance. Very complicated, but it is a linear connection. Or take a simple mathematical function that has a small domain, let's say a set of 1, 3, and 5 of odd numbers, and you have a certain function on it, you say multiply by 2, and then you get an output set of 2, 6, and 10, a set of even numbers. So before moving on to the question, what these concepts of number and functions actually bring to the table apart from their logical derivation, I would just like to give some general remarks on how the history of mathematics itself and also philosophy of mathematics currently interprets these developments in formal theory. The question pops up and concerns us here is about the status and the nature of mathematical objects. Now, we have proposed here just the concept of number and the function. But what such a question actually implies can be separated into a two-part question. And that is the first, a question of the ontological nature of mathematical objects of theories. So the search to answer a question whether mathematical objects exist, and if so, how and where do they exist? In space, in time, and so on, or do they exist in nature or just ideally? Are they constructed universally by our minds or exist in some parallel worlds of ideas? Or are they only exhibited in positing of mathematical theories? And the second question is, of course, the question regarding the epistemological status of mathematical objects or theories. So to answer the questions such as how do we know these objects? How are they defined? What is their state of affairs, etc. Since mathematical objects are not tangible things, their determination has taken a really zigzagging route, which could be formulated speculatively something like the following. Mathematical objects do not exist at all because we cannot determine the place or space where they exist. Yet, they exist universally for everyone, and they're immediately comprehensible. Now, this is, of course, conditioned by the two factors that they are posited within a system of axioms and decided upon a set of rules. But this is just the formal aspect of objects and soon runs into difficulties immediately when we start dealing with infinite sets, when we introduce the axiom of choice, when we go into infinities or inaccessible cardinal numbers. So let me start with the ontological aspect. We know fairly well that the Greeks were not entirely in agreement on these issues. The ontological determination of mathematics itself starts at least from the Pythagoreans, who began questioning what is the status of geometrical objects, since they are objects living only in imagination, such as points that have no extension, lines that have no breadth, curves or angles. Now with Plato, it becomes a realm of mathematical things that is in between the world of perceivable things of the senses and the plane of ideas. Now, this distinctive in-betweenness is attributable to the fact that mathematical objects are perceivable both through senses in the physical world, but can also be imagined in the mind. An imagined circle, for instance, you You can think about it in the mind without seeing it, or a circle drawn on the table. Now, the same goes for numbers. And that is why already in Plato, numbers and numerals are distinguished into pure numbers, which can be called from today's perspective as sets or units, and countable numbers of, say, unequal units such as people or apples. And this is just another example of the two aspects approaching mathematical objects. And as you all pretty well know, Aristotle reverses Plato's outlook. Now only things perceivable through sense and sense perception have significance for being as such. Without the realm of ideas, mathematical objects become part of the analysis of physics, and they differ only in the mode of methodology employed in their inception. Therefore, the positing of existence of mathematical objects is assumed from their empirical sense perception. And what is the object of mathematical analysis is rather the mode of existence of these objects. So to carry out this mode, we need some operations at work. For instance, the process of abstraction or subtraction, the apharesis of particular properties of a given object to attain a primordial genus, a generic object, but not necessarily by creating a new one. There can be an already existing one. Now, the point is to abstract or subtract the material carriers of units, lines, circles, surfaces, etc., to deal freely with their abstract nature and abstract calculus. And this goes even more so when it comes to numbers or geometric shapes. This separation also goes hand in hand with Plato's chorismos, what he calls the Greek word for separation. In other words, with the gap that separates the realm of ideas and the sensible world. And in terms of mathematical objects, this meaning their form from their material basis. Now, as Plato operates with ideas, he can have objects detached or subtracted absolutely from their material basis, something Aristotle simply cannot have in his analysis. So therefore, he opts for a solution that obviates all of the attributes of mathematical objects to those sense perceived, and to what is the point here, to those that exist for him and therefore the ones that have being. However, he nonetheless leaves an option of their abstraction in the mind made by pure thought. Hence, not the existence of extramundane forms, but a different point of view as to their mode of existence in the mind. This is what he's trying to get. So let me shift now from the ontological to an epistemological determination. As to numbers, for Aristotle, only concrete units, say of marbles or pebbles, have existence, while the numbering itself is a complete construct of language. But immediately after Aristotle, Euclid hits, and he proposes his system of axioms, which is revolutionary, of course, at the time, and defines a new way, particularly of handling geometry. And with it, the view now shifts more towards idealizations rather than Aristotle's abstractions from mathematical objects, meaning it aims to posit propositions, theorems, lemmas, corollaries about these objects. Now, what Euclid achieves with this shift is to break with the necessity immanent to Aristotle's epistemology of science, where proofs, but also theorems themselves, either mathematical or similar, need to directly relate to sense perceived and experienced phenomena, which in turn has to be true to be valid for a particular underlying concept. And with this act, Euclid actually moves us back closer to Plato, to his world of in-between ideas and the real natural world, where idealizations can afford to be either true or false. For we do not know objects solely from experience. Rather, what is true or false is inferred from the propositions laid down about given objects. So with these new shifts and discoveries, I move now the period into early modern philosophy to Descartes' innate ideas of the mind, now recognize a structure different and that now recognize and structure different independently existing shapes such as points, lines, and triangles. But he does not link these ideas directly to Plato's. he calls common images of appearance of all things, of given species, but maintains that they should rather be perceived as singular objects, clear and distinct in our minds, of which we can know everything either by our own consciousness, that is our imagination, he takes geometry and arithmetic for such, or by those clearly and distinctively perceptible. But as with Plato, so too with Descartes, it remains still undetermined as to where these ideas actually reside. Is it only in and for consciousness, or also externally someplace? Now, in conclusion, the Cartesian rationalism characterizes, as far as mathematics is concerned, objects as ideas derived either through deduction from already known and past theorems of the past, or intuition from innate ideas of newly uncovered objects, which brings Descartes to analytic geometry, which today is founded exclusively on set theory and algebra. But to think of mathematical objects as innate ideas also implies that we are not in need of any kind of definitions, either intentional or extensional, since such mathematical objects are already familiar to us. They always were. This is a position held also by Pascal, and that he addressed this notion with primitive terms. Now let me remind you that we, at this point, still have no answer whether mathematical objects exist or not, nor do we possess any satisfactory account of how to validate truth predicates from these propositions. For Leibniz, this was not the case to be seriously troubled. He embraced the view that mathematics needs only necessary definitions and from which he can derive basic concepts and attain proofs. And this is why he supports the propositions also of type A equals A, the tautologies. But there is yet another crucial factor that arises from Leibniz and Newton, and that is his paving the way to the concept of function at that time. In his time, the mathematical curves were thought of having an existence of their own, that is, not being designed by any particular formula, and were not, on their own at least, attributed to any numerical or algebraic properties. Put simply, formulas do not draw curves, as we learn today, but rather curves induce equations. Geometrical shapes had their independent origins apart from their algebraic expressions. But from this, a third path also followed. Apart from geometric and algebraic impression of a formula, it was the logical definition of a function as a correspondence of mapping input-output feature that is today understood as one of the cornerstones of transition from classical to modern mathematics. Now, for the calculus of variables introduced by Leibniz and Newton, the key feature was to approach the infinitesimals, either large or small, indivisibles and differentials, but still not a true definition of a function. Leibniz first used it in 1673 to talk about the dependence of geometric quantities on the shape of a curve through constants, variables, and parameters. But it was in the correspondence with Johann Bernoulli in between 1694 and 1698 that the first definition arose from Bernoulli, and he says like this: one calls here function of a variable a quantity composed in any manner whatsoever of this variable and of constants. And with any manner, he thinks about algebraic formula. And the history of function then goes on with Leonhard Euler, which immediately, a couple of decades later, and who happens to be Johann Bernoulli's student, makes a precise definition which is still valid today and underlies modern variations. And he says, a function of a variable quantity is an analytic expression composed in any manner from that variable quantity and numbers or constant quantities. So I will stop here with the discourse in history of mathematics, because we are now entering into 18th century, where on the one hand, detailed studies in various disciplines explode. In mathematics, in physics, and it's impossible to account for all. And on the other hand, we have new disciplines emerging, such as the study of commerce and moral sentiments that transform into political economy and later becomes economics. Now, what we will trace here is a specific lineage in the history of economics, that is, meaning of particular start with mathematical economics that actually precedes the economics as a theory or political economy before it was inaugurated with Adam Smith. And we will return to the contemporary mathematical handling of numbers and functions that also fundamentally impact economics. Now, when we mentioned Johann Bernoulli, there was also a certain Daniel Bernoulli, who happened to be his son. And apart from his applications of mathematics to mechanics, because as you well know, Bernoullis were a family that were 3 generations of extreme mathematical endeavors and new discoveries. And they made contributions to physics, to mechanics, to music, and also to economics. And he is probably the best known person in the 18th century to have used mathematical calculus to solve an economic problem, and quite complicated one. And this is before then, when the first really mathematical research work came out of Augustin Cournot's research. So what he did, he used the differential calculus and analytic geometry to derive a logarithmic function of unexpected diminishing returns. I will not go into details, but what was his real contribution, that with the formulaic description of income on wealth as a variable, Bernoulli demonstrated how to use a function, that is a function of expected utility, something that came as a revolution only in the 18th century, in the 19th century of the so-called marginal revolution of Jevons, Walras, and Menger, and is thought of as a major event in the history of economic thought. But I would like to return to our debate on currents in the history of mathematics, because we're now in a period of British empiricism on the rise with Bishop Berkeley, with David Hume and John Stuart Mill, and it goes hand in hand then with the development of political economy. But as for Hume, and so for John Stuart Mill, the mathematical world is a reflection of the real world. Such that for Hume, I quote, the idea of extension is entirely acquired from the senses of sight and feeling, end of quote. And Mill just simply rejects any independently existing mathematical objects. So there you have no number 10, only 10 apples, or 10 oranges, or 10 pebbles. And further on, arithmetic is entirely valid on deductive terms, and sense perceived objects of the natural real world are the only ones that are there. So what remains is an interesting revelation as to how poor actually did the empiricist camp actually fare with the epistemological domain of mathematics, and yet still manage to hold such a grip on applied sciences, and particularly in economics in the 20th century, a project that was also known then as logical empiricism, which endorsed economics. So as I already mentioned, due to the scope of investigations done and various disciplines, let alone mathematics in the 19th and 20th century, I do not wish to go in any of the details of these twists and turns, but I would much rather pay attention to those theories that shape the present-day mathematics, and then in consequence also shape now the mathematical economics. Now, stemming from Leibniz's logical deductivism, one has to immediately mention Frege's logicism and the system of logic that conveyed logical rules for arithmetic. It is, as you well know, a system where mathematical entities are explicitly definable using only concepts and objects from logic. And what also follows from this is that all logically true statements are mapped simultaneously to the truthness objects of mathematical theorems, since for Frege there is no sharp line to be drawn between logic or arithmetic. Now, what I would like to say that with Frege and the work done on fundamentals of set theory by Richard Dedekind, Bolzano, Peano, Cantor, Zermelo, Russell, Gödel, Skolem, and so on, the list is long. We had to come to the concurrent mathematical definition of a concept of a set, and consequently of the concepts of number and function, which now relies solely on this. So we learn independently from Bolzano and Cantor and Dedekind that sets are determined by their extensions, that is, by their elements alone, and generally not with their concepts, die Begriffe or the contentious manifolds, the Inbegriff. So Cantor did not have the option to determine the set by an explicit definition, but only with an implicit one, because the set is now an irreducible concept. And what was left to define it was the axiomatic approach. As to what sets are, however, Cantor gave a descriptive account of a set that is, I will quote a second edition from 1895, where he says, by a set we understand any combination M of certain well-defined objects of our intuition or our thinking, which are called elements of M, into a whole, end of quote. And Cantor's convictions were that the elements that are thought as one are things that belong to a created world, but that are either finite or transfinite, but not absolutely infinite. Those still belong to a different universe. And when we speak of functions, we are now in a position to state it in a category theory language, which is the most simple one now. And I quote one definition from Robert Goldblatt. A function is an association between objects, a correspondence that assigns to a given object one and only one other object. So what we have is an input-output device. We have on one hand arguments for inputs, and on the other side values and images for output. So that we get an argument x as an input and an f of x as a value of image of an argument by a given operation. In set theoretic terms, this can be said that we have a function a to b, where we have a the domain of a function and f as a subset of the set b. And then I can just quickly, and I don't bother you with this, define how a category now is defined in contemporary language. So we have a category that comprises of a collection of things called objects, a collection of things called arrows, a collection of operations assigning to each arrow a domain and a codomain, and then we have a collection of operations of composition assigning to each pair of functions their associative rules, so that you can combine functions f following g following c or whatever, and then we have an assignment to each object, also the identity arrow. And this is all there is to it to define a category in the mathematical world. But I will now just finally return to the relationship between mathematics and economics. And we have already suggested that a certain historical convergence take place sometime before the actual scientific discipline was amalgamated by Alfred Marshall's principle of economics and contemporary Samuelson's economic analysis. But what matters for history of economics thought is the fact that quite a few of the 18th century authors and works that have very significantly influenced the root of economics have been seriously omitted from books on history or principle of economics. It has become common grounds today that in the field of economics you see just a very strict division between those who point out the excessive usage of mathematics, that it is become a too abstract discipline detached from the real world and became oversimplified, and on the other hand, those who endorse mathematics absolutely. And these latter can be divided further into those who prefer the formalist side of mathematical economics and economics at large with axiomatic propositions, and those others who prefer more empirical data collection and a formal theory deduction that is being somehow approached in a two-way loop. So it informs, the empirical data informs formal theory then theorizes what the empirical outputs are and so on. And as you might imagine, as in mathematics, you also have in economics divisions of people stating they're Platonists, they're logicists, they're intuitionists, they're formalists, and other hybrid camps. So I do not wish to go into distinguishing these features, you all know them pretty well, but I would rather focus on what Fernando Zalamea, a Colombian philosopher and historian of mathematics, proposes for contemporary mathematics. That the divisions in mathematics, those divisions that range from idealistic to realistic assumptions about ontology and epistemology of its objects, are an immanent part of every philosophy of mathematics. it is through the mixtures, in the Albert Lautman's sense, that we can find a way towards a transitory ontology and epistemology by taking up category theory's analytical framework. What that means in practice is utilizing the concepts of functors, pre-sheaves, and sheaves. Just to explain very vulgarly, when we speak of when we talk about sheaves, we speak about a conceptual framework that can manipulate the realization of local singularities and variables of a certain model category, and by referring to a determinate system that is a base category. So you have a sort of a up and down movement between categories. So with the functors and sheaves as the most contemporary answer in mathematics on how to get from many to one. And with these major shifts in contemporary mathematics, there are also major repercussions in the discourse of economics. Throughout the majority of 20th century economics, it was deemed that it is a discipline of analyzing economic processes stemming from market and non-market forces to form an equilibrium state. But recently, however, at least in the second half or even later of the century, it shifted towards a system of relations, analyzing economic equilibria in terms of their properties, but also of mutual consistency checkups, of conditions, of assumptions, and validation of those models that they're built on. So we can conclude that the formalist camp has gained traction in the prevailing epistemic dominance on the field. And with what aim? To achieve maximum generality of application and conceptual integrity of analysis. But there is, however, something more to it. I'm of conviction that the mentioned meta-framework of sheaves and functors and natural transformations in mathematics has been developed now to a certain point, and with regard to our introductory remarks on the philosophical appropriation of mathematics, it can also shed new insights into the formalisms of economics itself. I think we have come in a position where morphisms, transformations, adjunctions, and the other instrumentaries have the capacity to deliver a new formalization of philosophical devices in a generalized topological space, topos, as you all well know. So this would be a place where we can deploy, for instance, Badiou's logic of beings appearing in a world, of Marx's notions of abstract labor, of exchange and surplus, or Castoriadis' magmatic structure to mapping a relationship with, for instance, a Debreu price system or a framework of asymmetric market relations or modeling decision-making, all in a unified framework. So this is the general idea. Now we're in a position where we can make these things talk. And that, for me, at least, is the task for the future critique of political economy, and most possibly a great challenge for other heterodox streams in economics. How to think philosophical and economic categories through such a unified model framework. So let me just conclude my thinking. It was and still is a grand achievement of those who introduced category theory, the theory of sheaves, the topos theory, and other new theoretizations in mathematics. But I would like to highlight here the work of William Lavier, who has passed away last year, unfortunately, and his brilliant work on categories theory capacity to axiomatize the localic and globalic objecthoods, to capture both the dynamic and static components of mathematical objects, of functions, morphisms, neighborhoods, states, points, surfaces, all into a one coherent body, showing not only how, as he says, objective dialectics can be paralleled with category theory, but also how adjunctions can emulate the unity of opposites in a dialectical process and mediate the dynamicism of two categories, namely of being and becoming, that move, that they ascend and descend through functors and natural transformations back and forth between different categories, say of static being or fluid becoming. It results in having an entity that is contradictorily fused on one level and actually sublated on another. So if I return just to our initial question, what is the nature and essence of mathematical objects? What contemporary mathematics shows, and is indeed well traced and elaborated by our contemporary philosophers, is that objects cease to be fixed, cease to be immovable, classical, and well-founded entities, but they are much rather in the process of transit and transformation in a web of multiple interrelationships. Multiplicities are the underlying objects of this transitory process. They constitute categories and process between them. Multiple syntaxes, multiple semantics with different logics mixed together. The question as to where these objects exist is relativized with regard to the regional and global ontologies. Indeed, when Badiou posits that number is a form of being and resides in the absolute, or when Castoriadis shies away from encyclic logic towards the indeterminate magmatic nature of being, one that is heterogeneously stratified and processual, we can more clearly understand their mutual positions through the lens of mathematics. And is it not, in the end, Deleuze, first and foremost with his mediations on fluxes with the encoded and decoded flows and codes, the interactions between poles, static and dynamic, and his oppositions of axiomatics and problematics, really a visionary of contemporary mathematics and the torchbearer of this conceptual implementation? One might ask, is there a second paradise awaiting behind this door? For mathematics, economics, philosophy, and who knows what else. Thank you.
Thank you. Any questions? Helmut?
Okay. Does it work? Yeah? Okay. Yeah, many thanks for your presentation. I think those are so crucially important questions. What you did, if I understood you correctly, is converging mathematical and philosophical trajectories in one way or another, and implying that there is a possibility of exchange or whatever. And I would object that a little bit if there is not more, that this question of, the possible formalization, the matem and all that is, if this works out so neatly in a certain way, and if there's not a, basic contradiction, also a logical or whatever contradiction in between mathematics and philosophy, and wouldn't it be interesting in engaging that kind of contradiction? That means, is a philosophy of mathematics possible at all, yeah? Or is it, the unfolding of pure functionalization, yeah? Leading up to algorithms and AI and whatever. So I would be very curious. That question comes from, my own, I had an investment in reconstructing, for example, biology in terms of biopolitics and so on and so forth. And in biology, there is the term life doesn't make any sense. It's a substantial term or substantialist term. It's all about functions. It's about heredity processes and things like that. But we wouldn't have biology without the term life, yeah, which separated itself from, physics and other, religious terms or whatever. So in the purely functionalist approach, we presuppose still a substantialist, category like life. And so my question would be, is that the case in mathematics as well? Is there something, and that would be if we presuppose this kind of substantialist idea, an idea not only of mathematical objects, but of mathematics itself, yeah? As an object of thought, would that be a possibility to also to understand and probably also to relativize the pure logic of functionalization?
Yes, thank you for that question. I mean, of course, there is a long history now of all modes of thought and thinking about how can we think objects of mathematics. And now I think we've come to the point where we need to consider are they really just products of our pure thought? And I think mathematics now is leaning towards this. Yes, of course, we can have substantialist theories and substantialist interpretations, but I think what the project also in philosophy and also elsewhere, and it was also for logicism, to do away with all this substantialist, so to have some substance from which, from which Aristotle actually starts, right? And I believe that because mathematics is actually a reflection of pure thought, that this is what it aims at, so that it can abstract from this, that it has a connection with, let's say, life sciences, in any sort of the term, that it can be just thought qua thought. And in that sense, I think that this is also what the project of these philosophers is actually how to subtract from that part and how to think just structures, and how can you put some dynamic into the categories which are only thought. So I guess, well, it pretty much depends where all this, just now research in mathematics, where it's going to end. What are the conclusions going to be like, and then the application, whether it will be a contradictory result of putting these discoveries into, let's say, biology, let's say, into economics, or whatever. But for me, for instance, this is not so much of a problem, because we're thinking in models, right? In economics, you think of models. You just devise a model and then you test it. And when you think about it, it is a theoretical concept in that sense. And then you first have to devise it theoretically, and then you test it if it works in principle, and then in practice as it is. So we now take these conclusions and we try to think something with them. So for me, this is just the first part, just trying to jump into something, and then we see where we come. If it's a dead end, it's a dead end. But as you know from history, we already tried a lot of things, going into different directions, and of course the theories that they couldn't hold up are lost. But there was a lot of theories that we tried in the history of philosophy or of mathematics, and they just failed, or chemistry or biology, you know. So that would be my answer. I think mathematics has here a sort of advantage of just brushing everything substantialist out of its vision, and then just move on and see if this makes sense, or if it doesn't, then it's just for them. It's consistent, it obliges Gödel's theorems, but that's it. That's for them is enough. That would be my reflection on that.
Yeah, thank you very much. I just have a true question on one point, because listening to you talk about these, let's say, the existence of the number on the one hand and the question of economy on the other hand, I was wondering, because you didn't mention it, and I was wondering what you do about the point or a certain development, let's say, in the history of economy which starts from, let's say, the Treaty of Bretton Woods in the late 70s, when the value of money was in fact disconnected from the gold standard. And you could argue that from that point on, the stock market and the entire industry of the stock market has taken on a certain turn of autonomy or autoteleological self-mechanism, let's put it like this. And then you could also say that nowadays, I mean, especially in things like high-frequency trading or so, you have actually a certain, a complete disconnection of the value from any physical resources. So, yeah. And so I was wondering whether this would fit into your argument or would rather not fit, because you could say, like, in a bit provocative manner, that the market realizes the number for itself without referring to any physical entity behind it.
Yeah, that's a good point. And actually, well, this goes actually back to Bernoulli, but it goes back to where the division of the labor of the theory of the labor value and the marginalist theories of the expected value of utility. This is where this comes out, because this is what I have here written, what Bernoulli says, for instance, and this is back in the 18th century, prior to any theorizing of economics, is that what actually matters is the expectation. This is what matters for utility, and then I think I have it here quoted. Let me just see if I have it. But actually, what it says, what it means is that value is derived from utility. And this is what Bernoulli says in the 18th century. He says that in 1738. There is no theory of nothing or what it is. And he said this already, and this is derived by him taking a sort of, it's called a St. Petersburg paradox, where you have a casino game and you flip the coin. And then what are the outcomes, and whether you would be willing to sell your lottery ticket if it is a lower amount than the one you get from the expectation. And this is where he derives that. So it is actually ingrained. What I'm trying to point out is that this thinking is actually ingrained well before when we are thinking of some intrinsic value that, for instance, some tangible assets have. So in economics, in economic theory, when you go really into history, then you see that it was really grounded on this, what we perceive of something. And we've come today still on these grounds. We haven't shifted that. And there was a shift when there was more like a substantialist theory now coming with the labor value with Smith. That comes somewhere in the early 19th century, let's say late 18th century with Smith, but it's not there really before that. And then it comes with Ricardo and gets a hold of it. So now when you come to post-Bretton Woods, and yes, well, this is now just, it has nothing to do with the fundamentals of either economic theory or anything else, ontologizing or whatever. It has to do with just the capitalist system reshaping itself. So when you detach from something, you get a wider scope, you get a better motion. So this is it's just financialization. This is what you get, so you can just expand your universe. Once they dropped the gold connection to money, the pegging, as it is called, it's just so that you can expand freely, you float freely. Of course, it has good sides to that, but of course, it has nothing to do with the fundamental, the intrinsic value of anything, so to speak. But I would say that this is now purely financial maneuvers. It has nothing to do with discovering anything significant or anything that will come to think a sort of a new theory of economics that will be beyond capitalist mode, right? So this is nothing that you can actually work on. It'll work now when you go into algorithmic trading, when the computers will start to do that all by their own, when you have the models now, language models, that will be, the trading systems are already made, but now they will become available to everybody. So everybody will be trading this by algorithm. It depends what it will come out, but it will still be the same system that we're in, only much bigger, much more grandiose and much more complicated and complex in terms of managing the system. This is for sure what it's going to be like.
Okay, so I thanks, first of all, for the paper. I had a question in particular about this moment that you're tracking between Descartes and Leibniz, in particular, the moment where, as you put it, the logical definition of function makes this move from the ancient to the modern. And one of the terms that comes in at that moment is definition. What I'm wondering about is if you're tracing the notion of number and function throughout this sort of very large history, what is the difference that you're seeing between the notion of definition and the notion of function? Maybe I'll just stop there and I can try to elaborate the question if it's not clear.
No, it's clear, but the answer is relatively, I mean, I really don't know if I know. Yeah.
Because let me just say, because one of the ways that you described the transition, for example, from Descartes to Leibniz, had to do with whether or not we need definitions.
Yeah.
And so I guess I was just wondering about what the relationship is to from definition to formula, if you see this as one of the formula sort of supplanting the definition, or what's the role of definition? I mean, I guess I'm really asking about the question of meaning in this moment.
I mean, well, I suppose it has to do with the development of mathematics of the time, because when they start realizing the differential calculus, and then they figure out when you put something in the numbers, when you calculate stuff, then you figure out that there is a sort of a connection, a relationship between the numbers. If you draw a linear or a I don't know, curve that is like a hyperbolic curve, then when they figure out that there is something to it, that they can formulate a sort of a relationship between the variables, how they draw themselves, I guess there is the point where they figured out that, okay, there is a sort of a connection there. As I mentioned, because you have the geometrical curves that they had on their own, but the differential is the moment when they figure out that they can calculate the function and how it is when it moves tangentially. And then when you get to that part, they figure out probably that they can write it down, that they can write down the function. So, and after that, the function just as a function, it has no meaning on its own. So then you need to have a sort of a, probably was the question, okay, we need to define what this, let's say, correlationship or correlation of these two variables is. Yeah, but I do not have the answer as to why the shift from function to definition, that I don't know. Why at that point did it occur that the definition was necessary outcome of that time? Yes, that I don't know.
Thank you very much for your speech. The function is seen as the link between an object as input and the object as output. But for us in psychoanalysis, I mean, it is very difficult to employ this, to use this formula, because we don't know the input and we don't know the output. We don't have these 2 points. And thus, the function must be defined quite in otherwise. And I would say it could be defined as relaunching, not knowing the starting point and not knowing the ending point. And this not knowing is very important. My question is, do you think that the mathematical categories, theory of categories, that is the purpose of the mathematical categories? And first question. And second question, do you think that this model can cope with this question without turning to the supposition that knowing everything, and so missing the point of this function of relaunching, not knowing the beginning and not knowing the end?
Yes, thank you. Well, I'm sorry, I'm not a mathematician, so it won't be exactly a mathematical answer, but I will try to put it like that. I mean, yes, absolutely. I think this is actually really applicable, because the category is now, in mathematical terms, so open that you can have open sets. So it is really a pure contingency of what you can put inside that, inside the input category or the output category. It pretty much depends on the function, the arrow, what it does with that something. You could call it a set or whatever, or category, which is more complex with much more structure and everything. But it is open, and you never really act in mathematics, and there is no need to know what is inside. Neither do you need to know what is outside. But it is the function that is determinable of the entire then edifice of what is going on. So in that sense, I suppose that it can be productively, I suppose. I mean, I'm not a psychoanalyst, so I don't know what actually do you seek at, because yeah, of course, it's a different story if you have like a more deterministic system or if you have a completely indeterminate system at hand. But I would suppose that this really is a universal framework. I mean, the best one that we've came up with yet, and it's worth trying out to test how it will behave in this type of situations, going from completely as a subjective an analysis of a certain subject, or as a completely objective process, as it is. Okay, it'll have different outputs, different elaborations, different discoveries in terms where I put it in economics, in terms of certain objectivities, or completely differently in a psychoanalytic setting. That would be my take. But
one maybe, Rok, and I have a very short question, then we'll have to start.
Yeah, thank you, Uroš. My question is, I think you dealt throughout your paper with like bilateral relations, like mathematics and philosophy, philosophy and mathematics, and then mathematics and economics. But is there what are the possibilities of the triangulation? So philosophy, economics, and mathematics. Can something be done in that field?
Well, this is actually what should be the outcome of this. I mean, you must give credit, I mean, to Badiou, to Deleuze, or to Castoriadis. So the way how they put it and try to think, I mean, it's basically the bottom ground, what they try to put. And I mean, how they, particularly Badiou, how he tries to develop going from set theory to category theory, but also Deleuze taking differential calculus and Riemann spaces, which is of course the frontier. And taking all this together, I mean, it delivers a base from where then the applied sciences, which are all have to naturalize on something. I mean, you had like naturalized epistemology, economics was naturalized, biology was naturalized, everything. But in the essence, it is philosophy that needs to come up with the concepts, and you need to have some kind of logical apparatus, which is now in the domain of mathematics. And then you can build on this, make it a framework, go into everywhere place. Of course, not going into the theory of everything. That's not, because this is what category theory actually is really good at, or the theory of sheaves, then later on more developed, or the topos theory, that you can have some localic stuff and some globalic stuff, and you can shift them around. There is no particular point, there is no Cartesian coordinates there. They can move. And once you get into process, into the flux of this, then you can shift it. So in that sense, I think that it is possible to do the combinations as they are necessary for a certain objectivity. To do like an analysis of something that is objectively there, a reality that you want to take a model of or whatever. So I think it has prospects. I mean, it's uncharted territory, and I believe that we should, dig deeper into this relationship. That would be my...
Thank you very much. We'll stop at this point. I think it's been a very lively discussion.
Yes, thank you very much.
So we're going to have a lunch now, and there is again one more change of program, namely it's going to be the same as it was announced previously. So the first is Amanda, then me, then Helmut, and then Christian.